Welcome, folks. How are we feeling tonight? Woo! We're good? All right. Energy's there. That's fine. Welcome to Idea Series. So this is the first annual event for Idea Series that we've done. So thank you for joining us. We're just going to start with a territorial acknowledgement for this. So the University of Waterloo acknowledges that much of our work takes place on the traditional territory of the neutral, Anishinaabe, and Haudenosaunee peoples. Our main campus is situated on the Haldimand Tract, the land granted to the Six Nations that includes 6 miles on each side of the Grand River. Our active work towards reconciliation takes place across our campuses through research, learning, teaching, and community building, and is centralized within the Office of Indigenous Relations. So Idea Series, presented this to you right at the start, but what is it? So IDEA stands for Investigate, Demonstrate, Educate, and Accelerate. These are a series of talks that we want to do annually to inspire and show you what it's like to do science for real, bring in experts such as Dr. Donna Strickland, who we have today, who have a lifelong career of doing science, and give you an opportunity to ask them questions and explore what that life is like. We hope that you enjoy the talk. We've got a number of undergraduate students here who have prepared questions for Donna, so you'll get to kind of be a fly on the wall to their conversation, and then come towards the end, you'll have an opportunity to ask your own questions as well. So without any further ado, I also want to welcome Dr. Laura Deacon, Associate Dean, Teaching and Learning, to come and provide a welcome.
Thank you. Thanks, everybody. This has been a long time planning. Thank you to those in person, all those online. So this has been at least a couple years trying to organize this. Started with my dean at the time, who asked, how can we get students to interact with the experts on campus, not just the folks in their classroom? And it brought me back to when I was a PhD student at McGill University, and Harry Croto, the winner of 1996 award, walked into the lab and was walking and asking questions like, hey, what are you working on? And I was only been there a month, so panic sets in. I show him this flask of things that I'm working on. It's deep red colored liquid. I said, I don't really know what's going on here, and I honestly don't know what the next steps are. And his answer was actually really calming. It was like, well, this is science. You get the evidence, you evaluate, you decide what the next step is, and you do that as you go forward every time, with the understanding that you can't plan the end step right away. It doesn't work out really, and it hardly ever works out the way you think, but it worked out. And then you look back behind and you realize you're not traveling in a straight line. You've made a step of decisions that through time have taken you to places you didn't really think you'd be. Like I'd never thought I'd be here, right? So then I thought, we have a Nobel Prize winner on our campus, and what if we set up a situation where students could ask, hey, what's it like, those decisions that you make one at a time, and when you think back and you think forward, what's it like? So I'm hoping that you'll walk away with a chance to reevaluate your steps in science as we talk about other people's progress through this. So please welcome to the stage, or to our guest area, our winner, our Nobel Prize winner, Donna Strickland, please. And the students, please come forward. And our students from the Department of Physics are going to go and walk through this space. In the back of your mind, keep your questions ready, and you're going to get a chance to ask as well.
Hi, so my name is Emily, and I'm in my 1A term of Physics and Astronomy here at Waterloo.
Hi, I'm Ro, and I'm in 1A term of Physics.
Hi, I'm Ryan, and I'm in third year of Physics and Astronomy. And joining us today is Dr. Strickland.
I'm in my 27th year here.
To start off, could you please introduce yourself? Tell us all about your background and what you studied in your undergraduate years.
I have a mic, it's okay. All right, so I went to McMaster University back in 1977, and I studied engineering physics. And I went because 1/4 of engineering physics was lasers and electro-optics. And to me, that sounded too cool.
As undergraduate students, we often focus on the hard skills relevant to our fields. Are there any skills that you learned or courses that you took during the undergrad that, while not specifically relevant to your career or field of study, impacted you in an unexpected way in the future?
No, but what I would say is that I should have taken more English, because I'm writing my NCERT grant right now and it's killing me, and I hate writing. And I hate writing to this day, so I should have gotten over that hate of writing, because I don't think it matters what you do. You have to write, even if AI is going to do half of it for us. You'd have to know that it's good writing if you saw it. So I would say that's one of the skills I wish I'd learned. But otherwise, no. Okay, here's the one that killed me. You know, I shouldn't have let it kill me. Because I got the second highest mark in it, so it has nothing to do with marks, okay, that I ever got at university was in computer science. But that course, by the end of it, I said to all of my colleagues in my class, shoot me if ever I have to go near a computer again. And I pretty much refused to go near a computer again.
Thank you.
So university is difficult, especially as an undergrad when life has changed so drastically in every way. Has there ever been a time in your career as an undergraduate where you felt like so discouraged or you felt close to giving up?
Well, I never felt close to giving up. I considered giving up twice during grad school, but not during undergrad. So I did. I have seen this question. So I did think about it, because I had it pretty easy as an undergrad, but I did blow my first year exams, and that upset me. But not enough to make me want to quit, just mad. I was mostly mad at the chemistry department because I'm just going to even tell you why I blew it. The first exam, and we had full year courses. We had to study for the whole 8 months. We were on a semester system. And I only answered 2/3 of the chemistry final. And I'm usually somebody who walks out of the exam, a 3-hour exam, an hour early. So the fact that I didn't even finish it just blew my mind. And I thought, oh my goodness, I don't know anything about studying for university exams. And so then I couldn't study for the rest of them. And the only mark that went up was chemistry. So they knew too that, I only answered 2/3 of the exam, but I still got an 85, which means that exam was silly. And so it threw me, and that was too bad.
And like now as a researcher, were there any challenges or setbacks that you have faced? And if there were, how did you overcome them?
All the time. A lot of people make a big deal out about that my Nobel Prize is from my very first paper, but I was in my 4th year of grad school. Okay, so I had 3 years of failures where everything I tried did not work. And I still have more failures than successes as a professor doing research. So yeah, it's a nonstop thing in science to have failures.
All right. So I just want to go back to my first question for a second,
Okay.
for a follow-up, because I've always just wondered on a personal level of why lasers? Like, what brought you, like, what attracted you to lasers and like optics as a field?
Well, while my mother was still alive, I must have answered that question because she told me I was wrong in my answer. And she said, I'll give you my mother's answer first, and then I'll tell you what my answer is. Her answer is that when the Toronto Science Centre opened up, I was just a young kid, and my parents took their 3 kids to see it. My dad was an electrical engineer. And supposedly my dad said to the 3 kids, they actually had a big CO2 laser, which I couldn't believe in 1965, that in 1960, or maybe it wasn't 65, whatever year they opened, 69, it was in the 60s anyway, that they would even have a CO2 laser that was, lasers were just invented in 1960. And he said, this is the way of the future. We've got to see this. Okay, so Mom thinks that's what got me interested in lasers. I don't remember that though. So, but when I was looking to see where to go to university, and I couldn't decide between engineering and physics, and McMaster had an engineering physics program, that made sense. And then 1/4 of it being lasers, it was just a gut reaction. So you have to still remember that this is the 1970s. So you didn't see lasers. Now you can go and get them at a dollar store and have it as a cat toy, right? This is not something we could see in 1976. So it just sounded, really cool.
Nice. And then, for me as a student who's currently in the 3rd year, this one pertains close to me. But when did you decide to go to graduate school? Like, when did you think?
In elementary school. in elementary school, I heard somebody, it's older, obviously much older, but was going to go to grad school and get, and I said, what is a PhD? And I don't even know really what the answer was, but the way I remember, which is not really probably the way it was conversed to me, they said it's the ultimate in education. And even as an elementary school student, I knew I belonged in school, so I knew I was going to stay as long as I could. So I didn't know I would go into optics, but I knew I was going to stay in school.
Awesome.
I mean, the real problem is halfway through grad school, I did not go to grad school for a job. So I didn't know what I was going to do when I finished because my whole career goal was getting a PhD.
As an undergrad student, it's hard to expect what is expected for us to know in the future. Would you recommend that modern scientists try to broaden their knowledge and perspectives through understanding other disciplines? And if so, how might they do that?
I think it's up to the person, and a lot. We talk about this multidisciplinary a lot. We talk about all these things, but we can all only know so much. And so I still think we all really should work on learning what we really love to learn, because then you learn the most. And so there are still plenty of subjects you can do just deeper and deeper down and not have to know that much beyond, although it doesn't matter what you need to know, from knowing the math to knowing, you do need to know something outside it. And again, I'll talk to a lot of people doing multidisciplinary work, and they'll talk about all the many areas that they need to know, but it's not that different than being really hardcore physics, but still needing to know the next thing out, whether it's computer science or math or, maybe the quantum mechanics that would go with, whatever else you're doing. So there's a lot to know. And I think either you learn it deep or you learn it broad, but you can't do both. And you have to decide which one you want to do more.
Do you have a way of thinking or approaching problems that you believe has been important in both your academic career as well as your life?
Which one have I been more successful at? No, I don't know how I approach the problems. I still, and this is the way I describe it always to myself, is that I see physics as a puzzle, and I enjoy doing puzzles, whether it's Wordle now or a jigsaw puzzle or a crossword puzzle, or I don't care what kind. I like to do puzzles, and I think physics is just a great big giant puzzle waiting to be put together. The university's already built, but to me, even people studying the cosmos are really just doing a giant jigsaw puzzle, trying to figure out how the parts fit together. And so that's the way I see it. And so I probably approach all of the puzzles much the same way.
Which puzzle? Thank you.
So over your career, you have the opportunity to share your knowledge and your research with people that are at, different education levels. How do you determine the best way to communicate to a variety of audiences?
Yeah, well, okay. I was just talking to a dean of science at the last university I was at, and her comment to me was, I've actually watched you give your public talk online, and you're such an excellent speaker. You must be a fabulous teacher. Not if you look at Rate My Professor, I'm horrible. So it all depends on how you look at it. So first, okay, so this is what I do for my living now, is that I give my Nobel talk over and over and over again. And so that one I worked very hard on. Right, because I did know I was going to give it a lot. I also knew there was 1,500 people in the room where I gave the talk, and it sits on YouTube, right? And tens of thousands of people have now seen it. So you don't want that to be a poor talk. And I will say, and this is something I hope universities start to do more, because I don't think they do. I met the then president of this university the day I won, and he said, what can we do to help? And I said, I have to give a public talk, and I want to give a talk as good as Bill Phillips. He's the best. Okay. If you ever get a chance to see Bill Phillips give a physics talk, he's the best. And so they did give me 3 people from the communications team worked with me on that talk. And 2 things. One, I have these great view graphs, or whatever we call them now, PowerPoint slides. And I've had a student walk up to me and they go, how do you get your photons to dance? I said, I have no idea. I asked for dancing photons, I've got dancing photons. So they made beautiful slides for me that I have no ability to do. But also, I would describe what I want and they would do it wrong. And that would really make me realize, oh, I wasn't good at explaining that. And so I think it really helped me get a public talk ready by having these many conversations with people that weren't anywhere close to science, right? So that's So that's how you have to, I think you need that dialogue. And so I think it would be great if universities would start putting communications teams with a few speakers in every department. I don't think all scientists are meant to be public speakers. You know, we all have our skills, and some of us do and some of us don't on all the various skills. But I think that would be good because I would like science out in the public more. Whereas when you teach undergraduates, whether undergraduates would appreciate it or not, when I'm giving a public talk, I'm only explaining the story. I only want them to get why I did something, roughly how it's done, so they can understand these are the main points and what the result of it was. But it is a story. Whereas when you're teaching undergraduates and you're teaching a class that they're going to need in the next class, it's all about the details, and it's quite a different thing. And the difference is that people can walk out of a public talk just thinking, oh, that was interesting, and that's all they have to think. Whereas the students have to go, I really need to learn this, and most of the learning is on their own, right? And so then there's this whole dialogue between undergrads and professors that way, and this is the tough one, right? And also, when you ask me how I think about physics, I will tell you that almost every time I taught, the top students would come and say, I loved your class, I loved your class. Well, I think they think like I do, and so the way I teach is the way I think, and they think like I think, okay? And the other people that liked me as a teacher were the ones who would come to my help session, and they had to be willing to work on the board, and then I would see what they couldn't figure out, and then it was a puzzle to me to figure out why they were seeing it that way, which is not the way I would see it. And so we would have to have this whole conversation so that we met somewhere in the middle so I could really get what they were seeing or not seeing, and they could see it in their way, right? Because there's no one way to really see it. It's just eventually you have to get there. But it's hard for someone who doesn't see it that way to get it. And so this is it. So obviously it probably comes back then that there has to be a conversation. If you're really going to give somebody information, there probably has to be a two-way conversation.
So your research, which won you the Nobel Prize, has sort of had like a domino effect on a lot of different fields, and also like lasers as a whole.
And the latest Nobel Prize in attoseconds, but keep going.
But it's had a wide range of applications, such as like medical devices, like delicate machining of parts, and a wide other like array of knock-on effects, which really has helped revolutionize a lot of things. And for starters, it's just how is it from like the perspective of, oh yeah, this was the research that you've done, and seeing like how it's like affected a lot of stuff, like from your perspective, how has that been? And also, how do you think in general research in one area has, like, is there any other breakthroughs that we might not know about from the research that have had like unforeseen like knock-on effects throughout the world of science?
Okay, so first, the Nobel winners in a field of science get a lot more attention than they probably deserve. Because science is something that really, maybe Einstein did a lot, but even Einstein was just cogs in a wheel, right? We all just have our piece to play. Sometimes the pieces seem to jut out a little bit more and get noticed more. But, I mean, there was a lot of work, just on how light and matter interact, all the way to getting the lasers to people. The reason we started to work on CPA was because a lot of people in a lot of groups around the world were working on something called fiber optic pulse compression. And so that was sort of the basis of CPA. And then I've given my talk, and other people with CPA said, why would you use a fiber? We all use gratings now for the stretcher. And I go, well, because Oscar Martinez had not invented the grating stretcher until after I did CPA. And CPA would not have been the big deal it is if Peter Moulton at Lincoln Labs had not come up with a whole new laser gain medium titanium doped sapphire, which allows much shorter pulses than what we were doing. And so then it meant you could get the high peak power with even less energy, and the money is in the energy. So a lot more people could have these lasers. So you can only take your part so seriously. It requires a lot of people doing a lot of things, and it's a long chain from where it starts to where it is now, and it'll keep on going. So yes, it is always amazing to see something progress like that. But I'll also say people ask, where did the idea even come from eye surgery, which is sort of the main use of CPA. And it came from laser eye damage, right? Gerard's student at Michigan got the Ti-Sapphire beam in his eye, and it's because the lasers that we use at Rochester were infrared, so you couldn't see them if you took your goggles off or on, so you might as well leave them on and be safe. Whereas if you took your goggles off, you could see the red beam. It would look like a weak red beam because it was just in the tails of where the tails of your eye could see. And so you would lull yourself into not thinking it was the wicked beam that it was. And he got the laser beam in his eye, and so they had to go to the medical clinic on campus, because your eye will fill with blood. And it was just a very smart young ophthalmologist who saw that usually laser damage is thermal damage, and it would be a tear of the retina. This was a perfect round spot because it's a laser hammer, it's not thermal damage. But we weren't thinking about machining with this laser yet. And this very smart ophthalmologist asked Gerard, what kind of laser were you working with that would do that kind of damage? And then the two of them started and tried to see how it could be used in ophthalmology. So it's this whole meandering. It's not just you doing your physics and you getting out there. There's so many ways for it to meander through life.
Cool.
So as a science student, I'd like to say that I can see the beauty of studying science. How do you think being a scientist has influenced the way that you view your everyday life?
Yes, well, I had to give a talk, because a colleague asked me to, about science and religion. And I pointed out that my husband and I have a cottage on Lake Huron, and so we look west, and so we can watch beautiful sunsets when we're up there at night. And I say, as an optical scientist, I can tell you why the sky is blue. I can tell you why the clouds are white. I can tell you why the setting sun is red. I can tell you why the light scatters off the clouds. I can tell you the physics behind that whole sunset, but it doesn't stop me from sending out my cosmic thank you for such a beautiful sunset and to live in such a beautiful world. And so, do I like knowing everything because I'm a scientist? Well, I only know the physics parts, right? I still enjoy seeing the crocuses come up in the spring, but do I know the biology of it? No, I do not. And it doesn't stop me from enjoying that either. So, yeah, I don't know if it gives me more of an appreciation or not. I just, I think the world's an amazing place, and I just enjoy it. And the stuff I understand, I'm glad I understand it.
In your Nobel laureate interview, you said science is about questions, not the answers. You're wondering why something works the way it does. We don't have the answer. We have to have the right questions. Looking back, do you think you began asking the right questions as an undergraduate student, or did it come with time and training?
Oh, I think it does definitely come with time and training. I think this is, in a way, I would like to see our education system change a little bit on that. Because I think, it's not that we don't have to know all the science that's gone along, and so this is why we have to teach undergrads all the science that's already happened. And of course, it's also then easier to test, do you know what's already happened? But I think we have to get more and more of the questioning into the curriculum. I think we have to, and it probably doesn't matter what area of science it is, we have to start instilling people with, what don't we know yet? What would the questions be? Why can't we do this yet? And start stepping forward. But again, it's not until you really start doing research, and probably at the graduate level, that you really start pushing yourself to ask that question, why, right? And so I think you do have to go to enough talks and hear the people saying, well, this was the question I had and I couldn't figure it out, and this is the approach we took to try to figure it out, until it starts to sink in a bit. That's at least the way I saw it.
And for our final questions, what advice would you give to students who are beginning to find right questions and want to pursue them as early scientists?
Well, first, I think that undergrads should definitely, anybody who thinks they really want to go on into science should start doing research projects probably. I started after my second year, so the earlier, probably the better. Well, also I knew I wanted to travel around Europe after fourth year, so that summer was already gone. I also think that's a good thing to do when you're young. It doesn't have to be Europe, it can just be anywhere. But I think it really helps you to see what's out there, right? I got to go to the National Research Council and really enjoyed it the one summer. So that I think is important, and I think it really helps you sort of start to realize what science is, because it's not what it's like as an undergrad. And so it gives you a bit of a flavor as to what science really is, if you can try that out. And you know, the world of science is big, so you want to see if you can do things. I mean, one of the top undergrads that I had the pleasure of working with in my lab, and he worked with me the summer after first year, he took his co-op terms and worked in a different area of physics every single co-op term, just to see which area of science he liked. So he was very smart from just, you know, doing science, but he also, I thought, really had a good plan to figure out, you know, how will I know? Unfortunately, for as smart as he is, he chose not to stay in science after his PhD at Stanford, but what are you going to do?
Thank you.
All right, so that's our last question from the panel. Just give a round of applause for our whole panel. All right, folks, so now it's your opportunity to ask a question of Dr. Donna Strickland or anybody else who's up at the front here of what's come to your mind during this talk, or what questions do you have about doing science in general? And I think we've got a couple of mic runners as well, so we can get these microphones out to you. All right. Somebody want to start us off? Yep, one right here.
Hi. So physics is a subject which intimidates a lot of people. I've seen many students who wanted to do physics but is scared of losing marks or things like that. So especially being in a male-dominated field, has physics ever intimidated you? And if yes, how did you overcome that?
No, I'm only good at math and physics, so I couldn't do anything else. So that's, I knew I belonged there. But I get that it's intimidating, and it is because, as they say, it's the non-intuitive subject, right? Unfortunately or fortunately, our best learning years are when we're young, right? And we're all going to learn more like Aristotle, right? Newton doesn't even make sense to us, because when you learn to crawl, you know you have to keep pushing yourself to keep moving. And so this is the real problem with physics, is that it's almost ingrained in your soul that one must use force just to keep moving. And then when we try to teach Newtonian mechanics, that says that's wrong. But this is the problem, is that other people are teaching you things and you don't innately think it's wrong. And so even when you first read a problem, you have a gut reaction to it, and then you have to tell yourself, no, I've got to think like Newton, until you take quantum mechanics, and then you have to think like Schrodinger or somebody else, Heisenberg. And so this is the problem with physics, right? But once you get over that, and once you start thinking, I can think like Newton too, right? Because it just you have to get your mind around it. I think it's a shame that people worry too much about their grades. I get why they have to, you know, but, and hopefully we're doing better with physics education research. I mean, most other sciences are following what we do with physics education research, because we are considered to be the hardest. But I'll also tell you, it's also just this, I think, almost a gut reaction too, that it's okay to say I can't do math or I can't do physics. But I was at a thing sometime this year, and there was 9 Nobel laureates, 3 from each of the areas of the 3 sciences that you get Nobel Prizes for. And all of the biologists had no problem saying, well, of course I couldn't follow your talk. But they got up and just went on and on about mitosis and blah, blah. And I went, well, what the hell? Do you think I can learn that? I don't know why you think I would know that, you know? And yet somehow it's not okay for us to say, well, I don't have a clue what you just said either. I did say that to them. If they said it to me, right on back at you. And so I think some of it is that physics gets a bad rap, right? And biology, you're supposed to just know. I was like, well, I don't know. I mean, I never even took grade 11 biology because blood makes me, and in grade 9 and 10, we had to cut up a frog and cut up a fish, and that was more than enough for me. So, you know, this is the idea, is that, you know, well, you should know it because everybody knows biology and nobody knows physics, right? And we should just get around that because there's no reason for it, really.
Yeah, and one more question. were you expecting to win a Nobel Prize?
No.
Like after giving the talk, were you confident that this is coming your way, or were you like really baffled?
After
to
giving the
know?
talk, what do you mean?
Like after presenting your idea, like
As
did
a
you
grad
know
student?
that? Yeah. Like were you like
No.
after, presenting the idea of your invention, were you
Well, it
expecting
was my
this?
supervisor's idea, it wasn't my idea. I made it work, but it was his idea.
But still, like, did you see it coming, or?
No. But I wouldn't say like no completely. I mean, no at that time. And also, I think we would not have won the Nobel Prize, as I said, if titanium doped sapphire had not been invented. And we did not know that that was being invented while we did this work. So we presented this work without knowing at all that Ti sapphire was right around the corner. So you couldn't know that. We thought that it was really going to be for the big lasers that sit in 5 or 6 huge laser institutes around the world. Now, along the way, and actually one of the guys who just won this year, Pierre Agostini, I saw him at a conference in the summer of 2018. And I'm walking out as he's walking in, and he sees me. He goes, "Donna, haven't you won that Nobel Prize yet?" And I went, "No." And so then he congratulated me. I said, did you know something I didn't know? And he goes, "I was just kidding you, Donna. I was just kidding you." So I had a joke with him back when he won, too. Because he wasn't expecting it at all either, right? Unfortunately, it was my postdoc supervisor we thought we'd get for nanoseconds, but Pierre got it. I'm happy for Pierre to get it. I'm just sad that Paul didn't. So no, it's a crapshoot to get a Nobel Prize. Although I will tell you, maybe I shouldn't say that, because you're not recording, you're just live streaming. Are you recording this or live streaming?
There's
Then
both.
I'll be careful what I say.
Thank you.
Another question on this side of the room. Yep.
Other than curiosity, was there anything else driving you for your research, for your Nobel Prize? Like any other factors?
Well, what does that mean? I'll tell you how I meandered to that. Like, that's all I can tell you. The first week I was in Rochester, I went to Donuts, which was before the colloquium, and everybody said you have to go to Donuts. And as a Canadian, obviously, we're going to go to Donuts. I was in the United States, but they had them anyway. And a fellow Canadian, because I wear an iron ring, because I have an engineering degree from Canada, a fellow Canadian engineer saw the ring and walked over and said, "I heard there was another Canadian here." And so we talked, and I said, "Well, I want to study lasers." And he goes, "Then I know the guy for you." So that very first week in Rochester, he took me over and introduced me to Georges Moreau. And he will actually say now to people the best, and he said it before we won the Nobel Prize, the best thing he did for science was introduce Donna Strickland to Georges Moreau. So he's the one who introduced us. And I got to see the beautiful laser. There was this beautiful red and green laser, and obviously we weren't as laser safety conscious as we are now, or I wouldn't have gotten to see those two colors. But it was so beautiful that I just thought, how much fun would this be? And so that's how I got to Gerard's group. Then Gerard is the one who handed me the paper that said, "Do you want to study this high order harmonic generation? And if so, figure out how to do it." And that's what needed a high intensity laser. So then we had to start, and this is why it was the second thing that we tried for making a high intensity laser. The first one didn't work. So, and then I had to do other things for the PhD that also didn't work. So that's how we went.
Hi, Donna. Thank you for your presence here. I'm wondering, like the Nobel Prize is awarded like for one insight or one sort of like invention, in a point in time. I'm wondering why don't they award it say for a lifetime of achievement rather than just a point in time, one thing?
Because the way it's written in Nobel's will. Now, if you look at some of them, though, there are some that are more lifetime achievement than that. But the way that Nobel wrote it in his will, and it's still his money that they're giving away, not the economics one, that's not really a Nobel Prize, says that it's, and they don't go exactly like he says, because it would be hard to do. The Nobel Prize says that it's supposed to be for the physics or whatever, but the physics prize should be for the physics done in the previous year that had the most impact on mankind.
But what about say if the career that has the most impact every year awarded, wouldn't that be more for a whole lifetime of achievement?
Well, there are ideas that really should be able to point to one thing. I mean, it makes it different than all the other ones, too. There's a lot of lifetime achievement awards. This is the one that's different than that.
All right. Another one on the far side of the back of the room there.
So you talked about how when you were younger, lasers were kind of rare and more of an exotic machine, and now they're ubiquitous in the dollar store. What do you think is going to be the most exciting area of optics or photonics coming up that might explode in the same way?
Oh, hard to say. I mean, you're right. The difference is that they're everywhere, right? Even short pulse lasers are being used everywhere, whether it's to go down to attoseconds or up to X-rays, or the only thing I ever talk about in my talk of what I want to see before I die is us break the vacuum. And we'll see if we can do it. And really only for the fun of it, right? There may not be any good science reason to do it, but then on the other hand, there might be, right? Until you do it, you don't know what's going to happen. So I don't know, you know. Gerard keeps talking about how he had me go, and it was a long time ago, so it's probably not going to happen. Can we beat CERN? Can lasers get so powerful and accelerate particles better than the next thing of CERN? Could we do that? Don't know. That kind of thing. But it's everywhere, right? I mean, there's like 1 million lasers in every data center. They're just everywhere. And we're still trying to get those on the chips, or at least how to get the light from the diode, to the chip and back, so that we can do it quicker and faster and smaller and cheaper.
Hi. So you alluded to a moment in graduate school where you thought you almost might quit. Are there some words of wisdom you might have for folks who struggle, and maybe walk us through how you found your way after that?
I only remember the one time, and I don't remember which of the 2 times it was, but I know that I came home, and it was probably something like American Thanksgiving, or it was an American holiday, so my family was all at work. And so I remember I turned on the TV, and it was a documentary about the National Ballet School in Toronto. And the head of that National Ballet School at that time said, I always tell the incoming class, if you can imagine doing anything else, go do it. This is too hard. You won't stay with it. And I went, ooh, every PhD student should be told that. And so then that's what I just sat there and went, well, okay, what else can I imagine doing? Nope, nothing. I guess I have to go back. That's what it was, yeah. She needs a microphone.
Hi, Dr. Strickland. My question to you is, who has been your role model, I guess, in your childhood or like in your scientific journey now?
Well, it's probably my mother. My mother was always the one who told me, don't let anybody else tell you. She wanted to go to math. I mean, she came from a small farming village, Milverton. Some of you might actually come from it. It's not far from here. And there was just 1,000 people in her little farming village. And her brother inherited the farm. The father, unfortunately, died young. But the 2 girls, if you can imagine, in the 1940s, went to university. And her sister wanted to do medicine and ended up in nursing because she was a female. And mom wanted to do math, and she ended up in arts because she was told that's what women should do. And so she, I grew up here and said, don't let anybody ever tell you what to do. You know best what you should do. So I would say my mom was my role model. Now, when people ask me, for scientific role model, and I was just speaking at the 60th anniversary of Maria Goeppert-Mayer's Nobel Prize, so the second woman to win. I mean, it was funny that when I wrote my thesis, I cite her work. I cite her graduate work and my graduate work. But I actually did, it was just M. Goeppert-Mayer. It was written in German. I had to go to this attic of a library back in those days to even find this paper. I could only read the math anyway because it was in German. And it was just M. Goeppert-Mayer. And it didn't even occur to me that she would be a woman, right? And so in my thesis, I wrote M. Goeppert-Mayer does this, and then the next sentence was he. And one of the readers, stroked a line through it and went, shame on you, Donna, and wrote that big, and then, she. And so then I actually read a journal article about her, a magazine article about her. And it was amazing that she loved her science so much. Obviously, she was brilliant. And she started a whole new field as a graduate student, right? She did not win the Nobel Prize for that. She did something else for a Nobel Prize in her 50s. And in the 50s, I don't know that she was 50s. And but she'd married a PhD chemist, and he got jobs at good places, and so she followed him. And the only type of job she could get as a woman was to be a secretary. There were places that would let her be a half-time secretary and let her use the office for her theoretical research, and she was willing to do that to keep it going. And so I just thought that's pretty amazing that you love your science so much that you're going to do it even though nobody's even willing to pay you to do it. So eventually she was being paid at Oregon National Lab when she did her Nobel Prize winning work, right? But I'll also tell you the funny thing is that when she was one of the first professors at the University of San Diego. It's about the same age as this university. So she went there around 1960, and she won in 63. And the newspaper headline the day she won was, San Diego housewife wins a Nobel Prize. And that's because in those days, you could work if you were a woman, but you better show that you were doing all of your womanly duties too, right? And so that's, it's incredible, and things have changed quite a bit since then. But so I would say she's probably my role model anyway.
That's really inspirational. Thank you.
Right. Yep, right on the second row there.
Can you hear me? Oh, okay. I just want to ask, during perhaps your whole life, like that's in contact with physics, have you ever had a moment where doing your research you're like, maybe I'm not good enough for like doing or making the achievements I want to achieve? And how did you overcome that feeling, I guess, if you have?
Was I never good enough? I mean, there's times, like obviously, I was probably the only one in the group that took 4 years before she managed to get anything to work, right? And so I was frustrated watching all the other students go off to the conferences and get to do talks and stuff, but I don't know that I ever thought that I wasn't good enough to do it. I just thought, I'm not doing it the right way.
Okay.
Yeah.
Thank you.
Because like I said, if I wasn't good at physics, there was no other place for me, so.
Yeah, I want to ask, what is Professor Strickland working on right now?
Yeah, I'm writing my NCERC about that. Mostly because I travel most of the time now, so I'm not really doing much of anything. Ask my poor students. We are trying. It was funny, the week before the Nobel Prize was announced, I was down at Cornell. And I was down at Cornell because I am the director of undergrad labs, and I'm trying to get the undergrad labs switched around, although they've hired someone to do the work because I'm not here to do it. But there was a laser person down at Cornell, Frank Wise, and he had just given a talk that summer at Photonics North, which is the Canadian Photonics Conference. And so I said, I'm coming down to see Natasha Holmes, but can I come see your lab? And he had built this whole new type of fiber laser system. And so I decided the week before I won to get rid of all my CPAs and start building his fiber laser. So we've got this new type of fiber laser in my lab, and we're just trying to make it run not broad single color, but 2 colors, because there's a lot of nonlinear optics that needs 2 colors to do it. And so that's what we're doing in our lab.
You've mentioned it a few times, but what exactly is a CPA?
Yeah, okay, so it's what I won the Nobel Prize for is called chirped pulse amplification. And so before the mid-1980s, which is when I did it, we had short pulse lasers, because that was the beautiful red and green laser that I saw was a short pulse laser, and even shorter than what my original laser was. And I was working at a fusion lab, so we had huge energy lasers in the same building, because fusion is an application that requires energy in to get energy out. But when they tried to put the short pulse into a big energy laser, they found out that they damaged the laser rods. Right? And this is also one of the reasons I refer to the CPA laser as a laser hammer. And actually at the time, because they were putting in big beams, and still they got these little tiny threads of damage all the way down the rod. And so it was quite surprising that this big beam would give this tiny damage. And so they had to figure it out, and it was a nonlinear optical effect happening inside the rod. And so this is why we could not put short pulses down these high energy rods, because we were destroying them. And so what we had to do was take a short pulse and stretch it And this is why I say the year we started doing this was 1984, because 1984 people were using fiber optic pulse compression. And so you can start with a laser that's not that short a pulse. You put it in a fiber. Through the nonlinear optics, you get all these colors, which you need to make a short pulse. And then once you have a bunch of colors, the long fiber makes the red travel faster than the blue. That's how you make the pulse very long, so it can safely be amplified up. And it's called chirped because a bird's chirp is the fact that the audio frequency changes in time. And so this is the optical frequency changing in time. It's the reddest color up front and the bluest color at the back. I mean, my laser was all infrared, so it's not red or blue, but it's the longest wavelength to the shortest wavelength. And so by stretching the pulse, you take the photon density low. And now you can amplify it up and keep the photon density low enough that nonlinear optics won't happen. And then when it's outside the amplifier, you put it through a compressor. And it's, my day it was air, but now the most powerful lasers use vacuum, because even air is a nonlinear medium for the most powerful lasers. And eventually vacuum will be also a nonlinear medium, but when we get to 10 to the 29 watts per square centimeter. We're at 10 to the 23 watts per square centimeter right now. So that's what it is, chirped pulse amplification. We could have called it stretched pulse amplification, but it just doesn't sound as nice.
Thank you.
Hi, Professor. I have a question which let me feel confused for a long time. And from my perspective, I think some subjects like physics and chemistry, these kind of subjects based on experiments. And when we design experiments, it can be a lot of steps. And after all those kind of steps, we get funding or get a result. And for each subject, we may do some, analysis by using characterization machines. For example, the XRD or the TEM to identify whether I did a rising or not. And sometimes we may make a self-check and may find the design of the experiment is right, but for the results, which could be just on the upside of what I had learned. And for the research, just as what you said is, when we find the result, we trying to use our knowledge and theory, what we have learned to explain it, why it is happen, even though sometimes the result is just out of control. We want to know why. And so this really makes me confused because sometimes I'm not, I didn't know that I trying to creating the false knowledge or doing something else. I guess that you have already doing research for so many years, so perhaps you also experience the similar situations. So how to deal with this? And
so what exactly is your question? You're wondering if things go wrong, are you really?
That is, we want to explain the result, and sometimes the result, we will identify that, every procedure is true, and sometimes the result is just,
wrong.
To the opposite of what, what we learned.
Okay. So first I want to thank you for saying that physics starts with experiment, because the last place I was, they were just insistent that physics started with theory. I went, no. Because theory, it can go either way, though. Sometimes the theorists are out ahead of us, and sometimes the experimentalists are out in front. And you can take it from either way. Obviously, if you're going to get a Nobel Prize, you better get an experiment done, because the theorists by themselves aren't supposed to get it. This is why Stephen Hawking never got a Nobel Prize. So I will also tell you that when I did the work with the first thing done with CPA was this multiphoton ionization. And it was a professor that had come down from the Université Laval in Quebec City. He wanted to be the first to use CPA. And so we did this multiphoton ionization work, and he thought it should be this theory or that theory, right? And it didn't match either theory. And we didn't know why it was at all. And actually, it was the reviewer of the paper, turned out to be a good friend of mine, but he didn't even let me know that he was the reviewer of the paper. And we asked if he wanted to have his name on the paper, supposedly. I had already got started my postdoc by this time. And he said no. So his name is not on the paper, but we used his explanation anyway, even though when he reviewed the paper, he sent us even a graph that we could use to show that he was right, that his idea was right. So, again, you have to But I had made sure that the way I took the data was as correct as it could be. That's all I could do as an experimentalist. I triple-checked, double-checked, did extra experiments to show that it really was the intensity, the laser intensity had to be the laser intensity I said it was. And so you put it out there and give it your best explanation. And again, you know, at no time do we ever absolutely have 100% of the thing figured out. There's always something new to figure out anyway, so you just have to keep going. I mean, if we actually have figured it out, then at some point there'll be some generation that there's no point in you guys studying science anymore because it'll all be figured out. And I don't think we'll ever get there.
Oh yes, that means that, you know, just by ensure every step is, you know, the steps of exploring the results, that is no problem. And so even though the finding is really different from what I have ever seen before, so it's...
That's usually the best. That's usually, you almost want to. I mean, and so again, when people say like it now cuts glass, it now cuts, this is because when CPA came along, it really changed how we understand how light and matter interacts, okay? So these are the things you want to find, especially as an experimentalist. You want to look at something that's just like totally brand new and needs to be explained. But it could just be one bad result, and this is why experiments need to be repeated and see if it's right or wrong.
Okay, thank you. Thank you very much.
Thank you. Now we'll come over to the side.
Yeah, thank you for the talk, Professor Strickland. So I have two questions. First one is, like as a student, were you good at following instructions, or were you more of a rebellious kind of a person, independent person? Like especially in grad school, where there's this idea that you have to consistently listen to your supervisor, and like sometimes did you follow your own mindset, or were you? Like,
not for long.
Not for long.
Wasn't allowed. Although he did apologize in my defense that he maybe should have let me do the one thing I wanted to do, but that was the only time I ever heard him say that. Was I rebellious? No, I'm not a rebellious type. Okay. I go along with the rules.
Okay. And the second question is, like, how important do you think is work-life balance? Because there's this idea that if we want to achieve something, we should, you know, like grind and stay awake till like 2 a.m., 3 a.m. Grad students are notorious for something like that.
Yeah.
So what's your opinion in this matter?
I worked very hard as a grad student, which is when I did the Nobel Prize winning work. So I haven't worked that hard since. But then again, my life's goal was to get a PhD. So that's why, there's no point in saying that's your life's goal and then not put your heart and soul in it. I did put my heart and soul into my PhD. In fact, actually, I'll tell you a story that the one night I was having a cup of coffee under the stairs, because that's where the coffee pot was at the laser lab. And the janitor came by, and we call them janitors and whatever. Anyway, and he said, "Can I ask you a personal question?" And I said, "I guess so." And he said, "Are you married?" So you do start wondering where this is going. And then I said, "No." And he said, "Well, if my wife told me every night she was going back to work, I wouldn't believe her. But every night, here you are." I guess that's why I'm not married. So I did work hard during my PhD.
Thank you.
All right, I think we've got time for two more. So yeah, go ahead.
Hi, Donna. So my question, you said that there were 2 times during your grad school that you almost gave up. So my question is, when was the most devastating time for your life that you almost gave up, and how you got through it, kind of?
One was early on. One was actually just a frustration with the administration because of money. And it was because I was honest, because I'm a rule follower. And I had put on my grad student application that I was expecting. There was a question, are you expecting a scholarship? And I was expecting an NSERC, right? Now, my fellow Canadian that was down there, not the one who introduced me, but a different one, he did not put it on. Therefore, he got the full NSERC plus the full stipend at that university, and I knew that he had that. I was told that I had to be kept even with all other students, and so I was to take, we only got paid $500 a month. So each term, and the NSERC comes in 3 installments. So the first term I was at Rochester, I took out $2,000 US and gave them the rest. But then the Canadian dollar goes down. So the next time when I took out the $2,000, I gave them less money. They did not register me for the whole term because they said I owed them $300. I said, no, I'm not going to make less than everybody because I'm actually bringing a scholarship. No. And they kept agreeing with me, but they kept saying they weren't the person that could fix it. And I must have seen 15 different people. I had a thing come and tell me that bill collector after me, they said, since you don't get to have health insurance because you haven't registered, and it just kept piling up. And I'd already taken my exams of the second term before somebody finally figured that out. And it was really just starting to annoy the heck out of me. And I was just thinking, I'll just go back home to Canada and, take my NSERC and leave it. So anyways, so what happened? So I had to take my qualifying exam, which was the 3 days of the week before Labor Day. So I got a 5-day Labor Day weekend, and I did come home. So that may be, I can't remember if this is the time I saw that TV show or not, but I don't think so. I think it was the other time. And I remember even saying to myself, just put one foot in front of the other. You have to go back even if it's to quit. Just put one foot in front of the other and get back there. And then I came back, and I had done very well on my quals, even though no one could say it, but everybody hinted to me that I had. And it was just like boom, boom, boom. I thought Gerard would be yelling at me because he hadn't seen me for 5 weeks. And Gerard said, okay, I hear you were told you can't have a lab at the Institute anymore, so I've got you a lab here. I was told, you need a different advisor than me. I found so-and-so to be your advisor. And boom, 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 he went through all of the things that they were giving me a really hard time about and fixed them all up. I went, oh, okay. So then I stayed.
I see. So it's more like when you run into something that's devastating, would you say you're more like one step at a time person?
Yep.
And you're not like someone that gets anxious or like really devastated? You would...
No, I don't think I've ever been really devastated in my life.
You would say you're an optimist then?
I always, yes.
Okay, thank you.
Awesome, thank you. We've got time for one more question over here. Maybe right up at the top there.
You said your life goal was to get a PhD, and now you have a Nobel Prize. What's next?
Yeah, I guess I'm not really that goal-oriented, I don't have any big goals. I just am just hoping that life turns out well. Yeah. No, I know a lot of people seem to be very goal-oriented. Like when the very first press conference and somebody asked if I wanted to save the world, I went, no, I had no desire to save the world. So, no, a different place I said I'd like to have grandchildren, but that's really up to my kids, not me, so what are you going to do?
That's great. Thank you very much, Dr. Donna Strickland and her panelists, and give them all a round of applause.